When lives are on the line, your software has to work every time, under every condition. That's where certification comes in. Certification of real-time operating systems ensures they meet the strictest standards of safety, reliability, and performance. It's essential in industries like aerospace, medical devices, automotive, and railway systems, where failure is not an option. These certifications assess everything from deterministic behavior and fault tolerance to functional safety and documentation quality. In this lesson, we'll explore the pathways to certification, the industry standards that guide them, and the design and documentation practices you'll need to succeed. Certification isn't a checkbox. It's a commitment to safety, reliability, and trust in environments where failure simply isn't an option. Real-time operating systems that power airplanes, pacemakers, or train control systems must demonstrate behavior under even the toughest conditions. Power failures, sensor glitches, or peak workloads. Certification relies on rigorous verification and validation, including exhaustive tests, fault injection, and stress testing to prove that systems behave predictably when everything goes wrong. Key domains like aerospace, automotive, nuclear, rail, and healthcare require different standards, but all expect core capabilities: process compliance, strict engineering procedures, functional safety, safe failover states, deterministic behavior, timing guarantees, fault tolerance, graceful degradation, and documentation quality, complete traceability. Behind every certified RTOS is an engineering process built on discipline, transparency, and systemic assurance. Enough specification and evidentiary proof to stand up to independent audit and scrutiny. Standards are the backbone of RTOS certification. In aviation, DO 178C defines design assurance levels, AE, with the strictest level A requiring complete code coverage, deterministic execution, and formal verification. Every possible execution path needs visibility and control, especially for safety-critical systems like flight control. IEC 61508 serves as a generic foundation for many safety standards. It defines 4 safety integrity levels, SIL 1 to 4, addressing the entire safety life cycle, from hazard analysis to system validation. Automotive systems subscribe to ISO 26262, derived from IEC 61508. It uses automotive safety integrity levels, ASIL A through ASIL D, to categorize risks. Autonomous vehicle controllers, braking systems, and airbag modules often fall under ASIL D, demanding the highest levels of verification, isolation, and documentation. Each standard builds a layered defense: error prevention, detection, and mitigation, from static code analysis and fault injection to traceable requirement to test coverage. Understanding these standards is not just bureaucratic. It's part of engineering systems that can fail safely and predictably when lives depend on them. Certification is built on evidence, and that evidence starts with traceability. Every system requirement must be linked to design decisions, implementation modules, and test cases, forming a transparent web of evidence that can be audited. Hazard analysis, often using tools like failure modes and effects analysis, FMEA, maps out potential risks like missed deadline failures, memory corruption, or resource conflicts, and ensures each is mitigated with design controls or fallback procedures. The result is a documented path from identified hazard to system remedy. Configuration management ensures repeatability. Code, design, tests, and requirements must align precisely through version control. Artifacts must be tied to specific commit versions, making rollbacks, audits, and reproducibility not just possible, but routine. This discipline forms the backbone of certification, proving that the system under test truly matches what ended up running in the field down to the last byte. To achieve certification, your development process must generate a robust set of documentation. Every step must be visible and verifiable. This includes a software safety plan outlining safety objectives and the strategies you'll use to meet them, like unit tests, traceability matrices, and fault injection campaigns. A software design document must detail the RTOS kernel internals, module interactions, interrupt handling, and scheduling strategies, so auditors can understand why your design meets the timing and isolation requirements. Test specifications accompany this, defining exact test cases, expected outcomes, and verification methodologies like boundary testing, error testing, and stress testing. These need to cover not just correctness, but timing constraints and fault conditions. If you're using toolchains or code generators, you also need tool qualification records. These certify that your tools themselves are dependable, or at least controlled, with documented test results and performance verification. This level of rigor increases with criticality, especially for DO-178C Level A or ISO 26262 ASIL-D systems, where even a misbehaving compiler could invalidate the certification. Certification doesn't only demand documentation, it must be reflected in your system's architecture from day one. Deterministic scheduling mechanisms, such as fixed priority preemptive or time-sliced strategies, support temporal isolation, ensuring high-priority tasks execute exactly on schedule. Similarly, spatial isolation, enforced via MMUs or MPUs, prevents memory corruption across fault domains. Establishing memory partitions ensures that a failure in one task cannot escalate across boundaries. Effective error handling completes the defense in depth. Each task or module should have structured fault recovery, error logging, and safe shutdown procedures to contain failures. These practices are essential not just for robustness, but for certification compliance. In essence, your RTOS must be designed for certifiability, with timing guarantees, isolation, error containment, and full traceability baked into its architecture. A certified RTOS is not something you retrofit, it's something you engineer from the ground up, so that safety is an outcome of design, not an afterthought.